Hello, good morning. My name is Igor Kadota. I'm a PhD candidate at MIT in LIDS, and I'm going to present joint work with my advisor, Professor Igor. Today we're going to talk about WiFresh, a simple yet unconventional architecture for wireless networks that carry time-sensitive information. This is the outline of our talk. We're going to start by describing this large-scale monitoring system that runs on top of a wireless network. Then we're going to use the concept of information freshness, in particular the age of information metric, to model the system. And then we're going to go into theory and develop scheduling policies with performance guarantees in terms of age information using different mathematical tools. Finally, we're going to use our theoretical results to come up with a new architecture for wireless networks, and we're going to call this architecture WiFresh, and we're going to implement it in a network of programmable radios and show its impacts in real operating scenarios. So let's start with this monitoring system. So here you can consider a base station that is receiving position information from 4 mobile nodes. So each of those nodes move with a given velocity v1, v2, v3, v4, generates position information and sends that information to the base station. Then the base station relays the information to the remote monitor, and the remote monitor does not know the current position of the mobile nodes, but it has this less known position information and also a position uncertainty. We're going to describe this further in the next slide. So let's look at the system from the perspective of the communication network. So here you have a mobile node generating packets with a given rate, position information packets, and placing those packets in a queue. Then here, a node 4 is going to get the head of line packet and send it to the base station, and the base station is going to send it to the remote monitor. Once the remote monitor gets this packet, this less known position here is going to be updated somewhere closer to the car. It's not going to be a perfect match because there was some packet delay, right? There was a delay between generation and delivery. So the less known position is going to be updated somewhere closer to the car, and of course that the position uncertainty is going to be reduced because we have fresher information. Now, if we assume that no packet is transmitted in the next slots, then position uncertainty increases, and here we're going to have a packet transmission from car 3, and again, we have an update. So this is how the system works over time, and this system would work great if we had 4 cars in the network. However, when you scale the system for 10, 20, or 30 cars, then we're going to have problems. So here, consider this system, this large-scale monitoring system with Wi-Fi. And when I say Wi-Fi here, I just mean that here we're going to have a FIFO queue, so first in, first out queue. Whenever packets are generated, they are placed at the head of the line, and we're going to use random access to access the channel. And by this I mean that whenever a source has a packet for transmission, that source is going to select a random time in the future to transmit that packet. If this is the only car that transmits a packet, then this is going to be delivered to the base station. Otherwise, if multiple cars transmit at the same time, they select the same random time, then the base station is not going to receive any of those packets. Right? So what's the problem with scaling here? When you scale the system, all of those mobile nodes, they're going to share the same wireless channel, right? So when you scale it, you're going to have less transmission opportunity, and even beyond that, when you have random access, you're going to have a larger probability of packet collisions. So, and this also detracts from this transmission opportunity. So basically, when you scale the system, you're going to have less transmission opportunities. However, all of your nodes are going to be generating packets with the same rate, meaning that you're going to have more packets in your queue and a higher queuing delay. So now, look at this from the perspective of the remote monitor, right? You're scaling the system. Now you're going to have less packets per car, and you're also going to, the packets that you get, you're going to have a larger delay. This means that you're going to have outdated information at the remote monitor, so you're going to have a very large position uncertainty. That's a basic problem. And we're going to solve this problem by proposing WiFresh, which basically means to change from FIFO to LIFO. And so what does this mean, right? It's a less in, first out queue. So whenever packets are generated at the source, they skip the entire queue and they go to the head of the line. So whenever packets are, the head of the line packet is always going to be the freshest in the queue. And this is going to help a lot. And even beyond that, instead of random access, we're going to do scheduled transmissions. And this means that the base station is going to run a scheduling policy and send polling packets. Right? So selects car 4, send the poll packet, car 4 receives the polling packet, sends the data packet with the position information, the base station updates its belief about the network state, runs the scheduling policy again, selects the next car to poll. With those 2 very small changes from FIFO to LIFO, from random access to scheduled transmissions, we can improve position certainty by 500 times. So this is the key contribution of the paper, and I'm going to show you how we did this. One of the problems that we come up now, that we introduced by having WiFresh, is that we have those scheduled transmissions, right? And one quick key question here would be, which packet to schedule next? And that's the problem we're going to model, and then we're going to optimize for. So now, to talk about which source to schedule next, we're going to introduce a concept of age of information using this very simple system. So we have a source, a LIFO queue, a channel, and a destination, and I'm going to talk about this timeline here, right? So we're going to have a slotted time, and one slot is the time that it takes for the base station to transmit a poll packet and receive a data packet. So that's what we're going to call one slot, and this is going to be our unit of time. So the blue arrows are the times in which packets are generated at the source. The orange arrows are the times in which packets are delivered to the destination. So here you have the packet delay of the first packet delay of the second packet, inter-delivery times, and having this, the question that I would like to ask is, how old is the information at the destination? And this is where it matters, right? How fresh is the information here? And I'm going to plot here the age of information as a function of time. And let's consider this time slot here. This is the time in which the base station receives the first packet. So suppose that I'm the base station. I just received this packet. How old is my information? My information is as old as the information contained inside this packet. And this information was generated Z1 slots ago. So my information is Z1 slots old at this moment here. Now, if one slot goes by and I don't receive anything new, then my information is going to be aged by one slot. So my age information is going to be Z1 plus 1, Z1 plus 2, and so on, until I receive a new packet. And at this point here, my age information is going to be updated to Z2. And this is how age information evolves over time. Are there any questions about this? We're going to talk about this throughout the presentation. Okay, great. So how does this relate with position uncertainty? So consider this car here, right? So this is car 3. Here we are plotting age information of car 3 over time. And let's get this time t prime. At time t prime, the age information is age 3. So this means that the remote monitor, the information that the remote monitor has is the position of that car age 3 slots ago. So for age 3 slots, this car has been moving with velocity v3, and the remote monitor does not know where it is. So the position uncertainty is just velocity times age information. And this is how you relate position uncertainty with age information. And that's why we would like to minimize age information of this network. Right? And we're going to make this statement at the model a little bit more clear now. So here is the network model for our for our monitoring system. So here you have the M nodes, and here we're going to the base station and the remote monitor. We're going to have this assumption here that is just used for simplicity. In our papers, we assume stochastic arrivals or periodic arrivals. Here we're going to assume that packets are generated on demand. So whenever the base station posts this source is going to generate a new packet, and this packet is going to go to the head of the line, and it's going to go to the base station, to the remote monitor. Which means that packet delay is always one slot here. So when the age information is decreased, it's decreased to one slot. This is just a simplified assumption. In the papers, we don't have this. All results can be generalized. So with this assumption and with LIFO queues, here we have n sources and mobile nodes. Each of them is going to have a different priority or weight, and this is going to come up in our objective function. Each of them is going to have a different LIFO queue. They're all going to share the same wireless channel, and each of those links is going to have a different quality. And what do I mean by quality? So whenever the base station posts, for instance, base station posts source 1. Source 1 sends a data packet. This data packet is going to be received with probability P1. And with probability 1 minus P1, there's going to be a transmission error due to noise. So this is the quality of the links. And each source is going to be associated with a different age of information evolution, right? So we have different age of information evolutions, we have different weights, we have different quality of the links. The base station has to take into account all of this to decide which one is the next source that it wants to poll, in order to minimize this age information, in order to minimize the position uncertainty of your network. Let's make this statement a little bit more precise. Our goal is to find a transmission scheduling policy pi star that minimizes the expected weighted sum age of information. And this is this. I'm going to break it down. So you have age information, expected age information, multiplying by the priority, summing over all nodes, time, taking the time average. And here I'm taking the time horizon to infinity, and I'm assuming that this limit exists. So I want to find the transmission scheduling policy pi that minimizes this quantity. And I'm going to call the optimal age information J star. Right? Okay. So let's go to theory, let's go to scheduling policies with performance guarantees, right? But before I talk about scheduling policies, I'm going to talk about those performance guarantees. So first, let's focus on this lower bound. So I'm saying that you give me any network with number of nodes, priorities, and the quality of the links. So the optimal policy, the optimal age information cannot be lower than this lower bound, which is very neat. Right? This is our first result. The second result is performance guarantees. So I'm going to give you a policy pi. and you give me any network configuration that you want. And if I say that my policy pi is beta optimal, I mean that the performance of my policy pi is between lower bound and beta times the lower bound for any network that you want. This is the performance guarantee that I'm going to give you. And we're gonna do this for 3 different scheduling policies. So we randomize policy, max weight policy, and a width index policy. We're going to use different mathematical tools. Unfortunately, I cannot go through them during this talk. But using them, we can give you different performance guarantees for different scheduling policies. So this is the theoretical guarantee. We also simulate our results, and we show that actually the max weight policy is very close to optimal. So that's why we are going to implement this policy in our programmable radius. And I want to talk a little bit further about this policy. So how does it work? It's a very simple policy, actually. At the beginning of every times.t, the max weight policy is going to calculate this index for every source. So weight, quality of the link, age of information squared. So you're just going to calculate this for every source and select the source with highest value of index. And if you do this, simulation results show that you're going to be very close to optimal age of information, and we guarantee you mathematically that this policy is going to be twice, on the worst case, twice the optimal. Okay. So let's go a little further to system deployments. So we have those programmable radius. If you've been near Professor Muriano's office, you've seen them. They are on the table there. We have 10 sources, 10 programmable radius sending data to this base station. And the main challenge here is complexity of implementation, right? We cannot do scheduling decisions in milliseconds. We have to do them in microseconds if you want to achieve good results. And to do scheduling decisions in microsecond timescales, we cannot do anything on a CPU. We have to resort to our FPGAs, and we have to do things on a MAC layer. So this was the main challenge of this work. Another challenge was that in theory, we assume a bunch of things. We assume that we know, for instance, quality of the links. And that's something that we actually don't know in practice. So we had to implement algorithms to estimate quality of the links. And we also assumed that we had slots and clocks were all synchronized among radios, and that's also not true. So we had to deploy algorithms to do clock synchronization in our network. Just a little bit further on this, so in each of those radios, we're going to have a CPU and a FPGA, right? On the CPU, we implemented everything that was not time sensitive. On the FPGA, we implemented everything that was time sensitive. For instance, polling with max weight, we do all of that in the FPGA. LIFO queues, and there's actually a rather interesting thing about LIFO queues. They are very intuitive and they should work for this kind of application. But if you look into Linux, or if the Linux stack, or if you look into software-defined radios, programmable radios, you don't find LIFO queues ready for implementation. You cannot choose a queue to be 5 for LIFO. We had to implement LIFO queues from scratch. So they're not used in practical systems. We also implemented timestamp processing for clock synchronization and estimating parameters, meaning the quality of the links. So now let's go to the final part, which is some measurements. So we're going to have 10 sources generating packets of 150 bytes with the rate lambda. And we're going to compare WiFresh with Wi-Fi. And this is the comparison, which I thought was a very nice result. So we have a rate here of 100 packets per second, 500, 5,000. And here we have age of information of WiFresh, age of information of Wi-Fi. So WiFresh achieves 8 millisecond on average, 8 millisecond age of information or information freshness. Wi-Fi achieves 4.7 seconds, which is a 582 times improvement on age of information, which is the same as saying 582 times improvement on position uncertainty. So this is a slide that I borrowed from John Tsitsiklis, that what we did here was start with a motivation in a real-world problem, then we go to theory, we model it, we optimize it, and then we see its impact in a real-world application. So thank you very much for your time.
Will anyone ask questions?
What exactly was the Wi-Fi that you compared it against?
Right, I compare what is the name of what type?
What was the Wi-Fi
WiFresh
that you
compared it to? So the software-defined radios, they come with a Wi-Fi implementation, which is just the Wi-Fi that we see in the routers. So they actually claim that they can interoperate with the Wi-Fi in the routers.
And the question is, still doing LIFO, why have a queue? Once you send the newer message, the old ones are useless. You can throw them away.
Right, absolutely, yes, we can do that. But when you talk about throwing some messages away, which we could definitely do, it would not change our results. However, you might want to use older information, for instance, if you're doing position monitoring, you want to estimate future position of the cars. Maybe it's useful for you to have older packets, right? But you're absolutely right that we don't want to send, it would not change our results if we just drop all older packets in the queue. Then we will have a FIFO queue with one packet, and whenever a packet comes, you just drop the older one and replace it with the newest one. We can do that. Absolutely.
Okay, thank you, Igor.
Thank you.